Okay, so I'm going to take you through the process of actually doing LCA and step-by-step workshop here. And all this content is available on the venturewell.org/tools for design website. So start out there and you'll see this introduction page. This is a whole class on green design, but what we're interested in is life cycle assessment. So go to measuring sustainability and then life cycle assessment. So there's the main page just describing LCA with a PDF primer to read and various other info and links. But what we care about right now is the exercise. And this is going to step you through everything. We're not going to take 3 to 8 hours to do this right now. I'm going to give you a quick once over of this, and feel free to pause and rewind, replay whenever you need to during this video. It goes quite fast, and I'm assuming that you'll pause whenever you need to. But we'll start step by step. So step one, decide on your scope and boundaries, functional units. Now, every LCA needs a goal. We're all just going to decide that the goal here is to quickly estimate the priorities for eco-design. So we're not going to do a full-fledged detailed LCA. This is just a quick and dirty fast-track LCA so that we can decide on priorities for sustainable design. And then choosing your scope, what we will and won't consider. So we're going to do a refrigerator here. And that's going to include all the materials and manufacturing of the fridge, all the raw material extraction, and the transportation to get from the raw material and manufacturing to the user. And then it'll include the use phase, the electricity during life, and the disposal at end of life. But it's not going to include, let's say, the food that you put in the refrigerator or any other parts of that system. So it's going to be cradle to grave of the refrigerator itself, but not larger systems. And so then choosing the functional units so that we could make comparisons between other refrigerator designs. We could choose environmental impacts per hour of use. That would be a nice standard thing. But to make the math simpler on us, I think instead I'll choose environmental impacts per 15-year lifespan of the fridge with it operating 24 hours a day, 7 days a week. And just to make an additional comparison, or in case we wanted to compare this to smaller fridges, you might say, oh, we'll save energy by having a small fridge. We'll save materials by having a smaller fridge. That's fine. But just to make it a fair comparison, let's assume that I have a family and I'm storing food for several people, so I need like a cubic meter and a half of volume for storing food. So let's say my functional unit is environmental impacts per 15-year lifespan of the fridge holding a cubic meter and a half of food. And then next stage is listing your inventory. Now this is actually already done for us in this exercise because I have a downloadable PDF that you can use here. And this has all the materials and the quantities in both kilos and pounds, and the manufacturing methods. So steel is cold rolled, the iron is cast iron, the aluminum is extruded, etc. And it's got the transportation. Sorry, these are only in miles, not kilometers, but we can convert. And then lifetime usage. So it lasts for 15 years. That was our assumption. And it's used 24 hours a day, uses 70 watts of power on average. And so that works out to 613.2 kilowatt hours per year. And then at end of life, we'll choose landfill as the disposal. So that's it for your inventory. And obviously, if you're doing your own product, you'll have to assemble all that information. But this is just an exercise. We have it here for you. And then step 3, actually calculating your impacts and then figuring out your uncertainties or your scenarios for sensitivity analysis. And this is where you enter all the data. Now, you will not always know what materials to choose in the database, and the database will pretty much never have all the right materials that you want, so you're going to have to make some estimations. And sometimes you can deal with that by saying, I think it's these impacts plus or minus 50% or 100%. But sometimes you need to be a little more precise or a little more extreme and try out different scenarios of what if it's scenario A, what if it's scenario B, to test your assumptions and where you might be wrong. So you can either do this in LCA software, which is generally easier but less transparent. But since this is just a basic exercise, we're going to use this template here. So that will download. Okay, so that just downloaded there. So here's the template spreadsheet. Yours may look different. We update it sometimes. And usually they're blank. This has some data filled into it already. But you can see generally there's an area here for materials and manufacturing. And then here for all the transport of different life cycle stages. And then here is use. This could be energy use or water, other consumables, and then end of life, like landfill, recycling, incineration, etc. And then the first column here is the names of things. So what are the materials? What are the manufacturing methods? What kind of electricity use? End of life, etc. And then there's the eco-intensity of those things. So how many kilos of CO2 emission per kilo of material, or whatever eco-intensity we're using. Maybe we're using recipe points. And again, that varies by unit. Here it's per megajoule of energy used, and it can change. And then there's the quantity. So if it's materials, how many kilos of mass of that material, or with energy use, how many megajoules of energy, etc. And then there's items per functional unit. So how many of things are we counting here? So if we're just doing a simple refrigerator like we're doing, and we're saying that the functional unit is environmental impacts per 15-year lifetime of that refrigerator, then the number of refrigerators in that 15-year lifespan is just going to be 1. So you can see that there's 1 for all of these things. And yeah, we would make 1 for all of these as well. But if we were doing some comparison, let's say we're comparing one normal size fridge to 2 mini fridges, then if those mini fridges are both the same, we would type in the amount of mass for each one and then say that there is 2 of them to handle the same amount of functionality as the normal size refrigerator. Or if we have a different design scenario where the refrigerator is designed for really long life, it lasts twice as long as a normal refrigerator, then you need half as many fridges per 15-year lifespan. So we would say that this is 0.5 for all things, etc. And yeah, we could put that all through here as well. But I am just going to make it 1 for simplicity. Okay, and then the next row is uncertainty here, and then the final row is notes, which is, yeah, of where you can mention your data sources or different units other than kilograms or etc., etc. And you can see the graphs here. you'll see this graph here is giving a line item. So every item in the table here shows up as one line in this graph. And that's true for transport and energy and end of life as well. But then that can get a little complicated and overwhelming sometimes. So there's also this graph here, which consolidates everything in the materials and manufacturing part of the table, everything in transport, everything in use, and everything in end of life. So this one may just be easier to read at a glance. And you notice that there's these funny blurs at the end of the graphs. That is to demonstrate the uncertainty. That's visually graphing the uncertainty for you. So the best that LCA data ever is, with the most precise data that perfectly matches what's in the database, you're looking at plus or minus 10%. Okay, that's best case scenario. And so that would look like this. Okay, so you can see that in the graphs. But particularly in early stages of design, we may be making wild guesses here. We might have no idea. Our uncertainties might be plus or minus 100%. And that's totally fine. And you can see how that changes the graph here. But you can also see that for some things, like, okay, if these are all known plus or minus 50% and my transportation is plus or minus 100%, you can see in the overall graph that even though I have huge amounts of uncertainty, I can definitely tell that materials and manufacturing is a bigger impact than even the worst case transportation. So this is the purpose of including uncertainty in here, to make sure that you're acknowledging your guesses and uncertainties, but still being able to make intelligent decisions. Okay, so those are all the different columns of the spreadsheet. And then where do you actually get this data? Well, the mass you get from your bill of materials, the items per functional unit we already talked about, the uncertainty we already talked about. And if you're not sure what numbers to put in here, there's a little rubric here that tells you 10% for precise data and perfect database match, 30% for a plausible substitution, 100% for a wild guess. And you can actually be bigger than 100%. It just kind of breaks the graph a little bit, but you can do your own analysis to work with bigger uncertainties. So, okay, the one thing that we don't yet know where to get is the eco-intensity here, and that comes from any LCA database, but it just happens that we have an LCA database built into this spreadsheet. So it's in a different tab here. It's actually in two different tabs. There is the simplified version of it, where we have the IDEMAT database, and you can see it's just a long list of stuff, where some of these headings are electricity by fuel type, energy, electricity by country mix, or we have materials like water use or wood, or we have metals like non-ferrous metals and ferrous metals up above, like steel, etc. And we have glass, etc. So you can just look through for different materials here. The simple version of the database shows you all of these materials and energy and other processes, and it only shows you the eco-cost metric, or the carbon footprint, kilograms of CO2 equivalent, or the recipe endpoint H metric. And so recipe and eco-costs are single score methods that put together a whole bunch of different kinds of impacts. And then carbon footprint is the sort of simple thing that a lot of people understand. And if we look at the more detailed spreadsheet, that has all of the same materials and processes. It has all the same rows, but it has more columns. There's a lot more columns because we have all those environmental impact midpoints as well, like ionizing radiation, ozone depletion, acidification of various kinds, eutrophication of various kinds, human carcinogens, etc., etc. And those all add up to that same final recipe endpoint HA score that we have in the simple spreadsheet. So that's the same column right here. But yeah, so there's just more detail, but it's the same data. And then also notice that most of the materials are listed in units of kilograms, but some of them are not. Some of them are listed in units of square meters, or if we go down to energy, then the units are in megajoules. And yeah, there can sometimes be other units, but most of the time they are in kilograms. So, how do we enter the data for our refrigerator? Well, let's go back to the bill of materials and see that there was 47.6 kilos of steel, and it's primary steel, so virgin steel, not recycled. And we see down in the manufacturing section that it was cold rolled steel. So, okay, so the first material here will be steel. There was 47.6 kilos of that. And what's the eco-intensity of that? Well, if we look at the database, we can just go up and down looking for steel. Okay, so here's fiber materials, fuels, glass, laminates, metals. Here we go, steel. And actually, there's a whole bunch of steel. There's stainless steel, high-grade steel, high-temperature steel, low spring steel. But let's keep it simple here. Now, it said on the PDF that it was primary steel. That means totally virgin steel, not recycled steel. So it's not this steel. This says that it's 21% recycled, 21% secondary, which is sort of the average in Europe. And this is 100% secondary, so it's not that. This one is 44% secondary, recycled, so it's not that. So let's just say that it's this one and figure that that is probably 100% virgin steel. And so the impacts of that are 2.31 kilos of CO2 equivalent per kilo of material. So great, we can just type that in, 2.31. But one of the nice things about this all being in Excel is that we don't have to just type in flat numbers from a lookup table. We can make this a formula. If I type the equal sign and then click on that cell and then hit return, it still says 2.31. It's still that value, but if you look, it's a formula now where it's pointing to that sheet and that cell in the database. And so that's really nice because that can help you troubleshoot if something is weird, help you find bugs in your analysis. You can also do search and replace if you decide you want to change from analyzing carbon footprints to analyzing recipe points or whatnot. So it's just really nice. So, okay, so we've got the eco-intensity of the steel and we've got the mass of the steel, and the uncertainty, we can bring that down because we know probably what material it is. Let's say it's 20% uncertain because I was making a little bit of a guess, but I can say mostly known material and precisely known mass. Okay, so those are my notes there for those assumptions. So great, so that's it for steel. And then the manufacturing method for steel, it said was cold rolling. So this is the steel cold rolling, okay? And the mass of that is exactly the mass of the steel. So again, I can type equals and go to this cell and hit return. And then it's nice because if I update the mass of the steel, then it immediately updates the mass of the manufacturing method as well. And okay, cold rolling, so let's get the eco intensity of that. And you know, I could just browse for it, but I can search too. Let's just do a search for rolling. And boom, the first thing I get is rolling steel. Great. So that is 0.49. So okay, so the equal sign, and then click on that and hit return. Boom. Okay, 0.49. And the uncertainty of that, I think that was even better. So I'm going to say 10% because there was only one choice for cold rolling of steel. So I'm going to say precise mass and precise database match. Okay. And then what's next? Next is iron, and it says in the manufacturing methods that it's cast iron. Okay, so let's look for that. Okay, iron. Oh, and the mass was 4.5 kilos. Okay, and let's look up iron in the database here. So we've got, let's see, okay, steel, construction steel, cast steel, stainless steel, cast irons. Okay, so here we go. And notice that it says cast irons. It doesn't just say iron with casting as a different process listed later. This is including both the material and the manufacturing, the casting as well as the iron. Now, some database items have that and some don't. You just have to pay attention. But which cast iron do I want? There's a bunch. And okay, frankly, I don't know the difference between these. So I'm going to take a guess. And looking at their impacts do vary by quite a bit, you know, by like a factor of 2. So I think, you know, I could just pick one arbitrarily and stick a big uncertainty on it here. But again, one of the nice things about Excel, I can make a formula. I can say the eco-intensity is the average of all of these cast irons. Boop. And then for the uncertainty of that, I can say, I mean, I could just take a guess here and say, yeah, probably plus or minus 50%, that's fine. But again, I can do a formula. I can say the uncertainty is the standard deviation of all of these different cast irons. And boom. And as you can see, it's 48%, which is pretty much 50% anyway. So, but it's a little more precise, and that's a nice thing. So, and then for notes, guessed with average of all cast irons. Okay. And so we don't have time to do all of the materials and manufacturing methods here, but let me just do one more. The next one is aluminum. Okay, so aluminum. Okay, and it was 2.1 kilos of that. And okay, the eco-intensity, if I do search for aluminum, it does not find it because it uses the British spelling, so aluminium. Okay, but here we go. Aluminum primary, And so here are the impacts there. Okay, so equals, boom, enter. Okay, and here I'm going to say the uncertainty once again is quite good because it was a precise mass and a precise match in the database. So I'm just going to copy and paste that note. And then the manufacturing method for aluminum, it was extrusion. And so, okay, aluminum extrusion. And again, the mass is going to be the same as the mass of the material and the same number of items per functional unit. For uncertainty, let's see. So if we go back to the database here, for aluminum, let's see if any processing. Well, let's just do a search. Extruding aluminum is right here. So, okay, again, it is 0.68 kilos CO2 equivalent per kilo of material. And so we'll just put that in. Where did it go? There we go. Okay, and yeah, I think that uncertainty should be perfect for the same reason that we had before. And so that's all great. Now, you can see that we're kind of running out of space here, and our bill of materials is longer than this. So again, nice thing about Excel is that we can just expand this. We can just add a bunch of rows. You can just insert a row and then do that a bunch of times. Now, the one problem here is that the graphs don't automatically catch up when you add rows, because the graphs are actually not graphing what you're typing into the blue areas here. They're graphing what's in the gray area here and the gray areas over here. This is how we make the nice little uncertainty stacked bar. But that's fine. It's easy to catch that up. You just select all of these rows here and you copy and you paste downward, and that fills it all in. So now you'll see that if I type some random thing in here, okay, then you'll see that that it does enter it in here. There is a little bit of cleanup that needs to be done. You know, you need to merge across, and that's basically it. And then you're done. But I'm just going to delete that and move on. So, okay, so that's basically it for entering materials. There's just one other thing. If you look back at the bill of materials, you notice that the bottom item is other materials. What's that? Well, guess what? We don't know. And yes, that is intentional, because in the real world, you never know all of the materials in your product, and you'll just have to take a guess at some stuff and use your best judgment. What do you think else might be in a refrigerator? Maybe there's some electronics for a thermostat, or maybe there's a little LCD display or something. Who knows? You can take a best guess and see if it makes much of any difference. Like maybe if there is, let's say it's a circuit board. Okay, so printed wiring board. Okay, and the mass is 7 kilos. Okay, that's a lot. You're never going to have 7 kilos of circuit board in there unless it's some kind of super crazy computer. But let's say that there's, I don't know, 200 grams, 0.2 kilos of printed wiring board. Okay, so I do search here. printed, I think it's printed circuit board. Yeah, exactly. Printed circuit board, including ICs, that's the integrated circuits, that's the chips. So, okay, so, and it is per kilo, unlike some of these other things here that are per square meter or per piece, per item. But yes, okay, so 260, that is quite a high impact per kilo, but that is totally realistic as well. Okay, and let's say there's one of those, and uncertainty, I have no idea, plus minus 100%. And so that is a total guess. But yeah, so that might be some of the quote unquote other materials that you have. And right now it's hard to see much happening because there's this extra default data that is sitting in here that's making the graph big. You can kill that so you can actually see some of this. And I'll kill the energy too. So yeah, so you can see that even though this was a total guess, we can still probably say that the impacts of electronics in the fridge are almost certainly smaller than the impacts of the steel in the fridge, particularly when you add the manufacturing of the steel on top of it. So again, making informed decisions with lots of uncertainty. Okay, but speaking of transportation, let's get that in here. So if we go back to the bill of materials, what does it say? Okay, so it says that there's 6,000 miles of ocean freight transport. That is 10,000 kilometers. So I'm going to say that the distance is 10,000 kilometers. Okay. And what's the mass that's being transported? Right now, you'll see that there's this formula of everything here divided by 2 divided by 1,000. So that's basically assuming that everything in here is going to have a material line and a manufacturing process line. And so the masses will be multiplied by 2 just by entering them all twice. But as you can see from the data that we entered above, that's not true. And then the dividing by 1,000, that is because this is in units of tons, whereas this is in units of kilograms. So that we will keep. So I'm going to delete some of this, but I'm going to say that the mass is this plus this plus this plus this, and that all divided by 1,000 to convert it into tons. Okay, and then what is the eco-intensity of that? Well, let's look that up in the database. So let's do a search for freighter. Okay, train diesel freight. No, that's not what I want, but here's transport by water. And so, okay, barge, bulk carrier, okay, container ship. No, container feeder is not quite what we want. But yeah, container ship, this is one of those massive container ships. And you can see there's another container ship item here with different units. This is cubic meter kilometers versus ton kilometers. This is for things that are very lightweight, that are where the limiting factor is volume, and everything else is for when the limiting factor is weight. So that's why it's ton kilometers versus cubic meter kilometers. So, okay, container ship. So these are the impacts there. Okay, so we will type that in. Okay, and then the uncertainty, I think we can be pretty certain of that because we know the exact distance and it was a perfect match in the database. If you want, you can say that transport varies a lot more just because um, different things get shipped to different customers in different places. And so you could just say plus or minus 100% accounting for many customer locations. And that's fine. As you can see, it's such a tiny value that it does not make any difference. So could be 10 times that much freighter transport, doesn't matter. And then the next transport is rail. And okay, so let's say rail, and that was 500 miles, which is 800 kilometers. Okay. And then the mass per item, well, it's still an entire refrigerator. So I'm just going to say it's equal to the same mass that we had a minute ago. And then what are the environmental impacts per ton kilometer? Well, let's check that out. Okay, so rail, we have two options here, diesel in the USA and electric in Europe. So I'm going to take that one. Okay, so equals, boom. Okay, there we go. And again, I'm going to say the uncertainty is plus or minus 100% to account for different customers, whatever. And as you can see, once again, it doesn't matter. It's a total rounding error. And yeah, we could also enter in the truck transport that's in the bill of materials. I'm just going to move along here for the sake of time, but let's look in the bill of materials at the energy use. So, okay, there's 15 years of lifetime and 24 hours a day of use, and the power required is 70 watts, and the yearly power use 613.2 kilowatt hours per year. Okay, so now that is a useful number. The power and the hours per day, it's not actually super helpful, but the kilowatt hours per year, that is helpful. I can just take that and multiply it by the 15-year lifespan. So, okay, so how do I enter that data? I can either say that the amount per item equals 613.2 kilowatt hours per year, but remember in the database it's megajoules, so I need to multiply this by 3.6 to convert from kilowatt hours to megajoules. And I could also say that this is times 15 years of usage and then have one item per functional unit. Or I think it's a little cleaner to cut that out of here so that this is the energy use per year, and then I put the 15 years here. Either way is fine, but I think this is a little cleaner. But then what are the impacts of that? So if we look here, okay, electricity by fuel, electricity by country mix, that's more useful. So Western Europe, Netherlands, these are both industrial or for low voltage domestic use. So this is ordinary household electricity in the Netherlands. If you're in the US, it varies by region, and actually impacts vary a lot by whether you're on the West Coast or East Coast or South. So it'd be nicer to figure out your own electricity mix by what percentage is coal, what percentage is gas or nuclear or hydro, etc. But here in the Netherlands, it's very easy. I'm just going to use this one. So, okay, equals that. Okay, and for the uncertainty, I could say that it's just 10% because I did have the bill of materials giving me an exact number. But I mean, people's electricity use varies. People's refrigerator use varies from user to user. So I'm just gonna put in a 30% uncertainty, saying accounting for user variation. Okay. And then you'll see that immediately that completely blows out all the other impacts here. You can barely even see them. And yes, there were a lot more materials and manufacturing methods that we need to enter in, but spoiler alert, with a refrigerator, the energy use is just going to be the dominant impact for the life cycle, for the whole lifetime of the fridge. But for the sake of completeness, let's also get in the end of life as well. And so we do this material by material. So there's steel, there's iron, there's aluminum, printed wiring board. So we'll start with steel. Okay, and the mass per item, again, just going to use a formula for that. And what's the eco-intensity? Well, so the end of life, let's check the bill of materials. It says it's landfill. Okay, so if we go here and we landfill, okay, so waste treatment. Okay, yeah. So this whole area there's actually a lot of different waste handling scenarios here, particularly if you're doing incineration. There's a whole bunch of different options of incineration for energy, for heat, for electricity, for both. But we're keeping it simple and just going with landfill here. So, okay, so this is for organic, this is for inorganic, not biodegradable. Okay, steel is that, it's not biodegradable. And so here it is. It looks like the impacts are 0, which is actually quite common. As long as something isn't leaching nasty chemicals into the groundwater, it doesn't do a whole lot when sitting in a landfill. But okay, so there are the impacts there. And we can say that the uncertainty, let's say the uncertainty is plus or minus 100%, because let's say that this is vague landfill data. Okay, but yeah, still doesn't matter. And then we can do the same thing, end of life for material B, iron. Okay, so the eco-intensity, that's going to be the same because that was the same number for all materials. And then the mass of that is the mass of iron. And we can copy and paste the uncertainty in the notes. And you can just keep doing this for all the different materials. But feel free to put in recycling or incineration. It's, in different scenarios. This is one of the powerful things about LCA is that you can model all sorts of different scenarios. And in fact, this spreadsheet here that we give you for the template, it automatically includes a whole nother copy of those tables above to make it easy for you to make another model and then compare the two of them against each other down below. So feel free to do that. Or another easy way to do sensitivity analysis is to just make a copy of this entire tab. So move or copy, you create a copy, and yeah, LCA model number 2. And so then everything is already here, and then you can just say, okay, instead of steel, I'm doing, I don't know, stainless steel. And then you swap in a number for stainless steel. Or you say that this fridge is extremely energy efficient, and so it only uses, let's say, 313 kilowatt hours of electricity per year, and boom, you can immediately compare that to the first model by just switching back and forth between tabs in the spreadsheet. So that's also a handy way to do sensitivity analysis. And one of the reasons that you might do sensitivity analysis is if you have overlapping uncertainties in here so that you're not sure what your design priorities are. Like right here, we can very clearly see that energy use blows out anything else. But what if your electricity use was, oh yeah, I forgot to label that. What if your electricity use is 100% solar power? Okay, now what? Okay, so here's PV panels. So now let's look at what happens if we make these impacts equal to PV panel impacts. Boom. Now you can see that energy is still dominant, but it's not as dominant. So what if we had the energy use all solar power and we also used half as much electricity? It's still dominant. Okay, if we made it super efficient by using just a third as much electricity. Okay. And what if we accomplished that by using twice as much steel? Okay, so now there's a lot of overlap in these different bars here. And so now we would want to either get more precision on what's happening with either of these, or do just different design scenarios, which is exactly what I was doing here by saying, what if this, what if that? And you can see it live updating when you change the values, and I can just undo all the changes that I just did, and we'll go back to what we were originally modeling. And sometimes your sensitivity analysis will actually make you rethink the whole thing, the whole analysis. You might want to change your boundaries of what you're counting and what you're not counting. You might want to change your functional unit. That's fine. It's not a mistake. It's part of the iterative process of modeling your system in LCA. And the bottom line is what you're trying to get out of this analysis is, what are your priorities for sustainable design here? Should you be concentrating on making the fridge more energy efficient, or should you be concentrating on using less material or lower impact materials or a better end of life? And by the way, even if the end of life impacts are showing up as zero like they are now, that doesn't mean that it's okay to have a short-lived fridge that you throw away at the end of life. If you recycle the materials, you will lower the impacts of materials in manufacturing the next time around. And in fact, so you can see the score of some recycling showing up as negative. So like, let's say that the steel is, instead of landfill, the steel is recycled. Okay. Okay, so these are all materials, still materials. Okay, okay, waste treatment. Here we go. Recycling credit of materials. Great. So there is aluminum, copper, gold, lead, okay, steel. Okay, here we go. And you'll see that there is a negative number here. So if I type that into here, so this equals that negative 0.23. Okay, and so it's not enough to show up on here still because it's such a small impact. But if I delete energy use for a minute, then you can see it. And so that is pretty much it for the calculation phase. And as you were seeing, the analysis and interpretation goes hand in hand with that for that iterative process. But so the last part of the exercise here is a checklist for self-assessment. Just go through, did you do this? Did you do that? You can write this all up in a Word doc and paste in a screenshot of the spreadsheet. paste in the table with all the values that you entered in, and it's nice to expand the notes column so that you can see all the notes that you wrote there. Be very transparent about those details, especially when you were substituting one material with a proxy or making a guess or something like that. And then you write down what your conclusions were, what your sustainable design strategies are going to be as a result of these calculations. And that is pretty much it. That is LCA in a nutshell.